All right. This is the last of the new material. We're Thursday, week 7. This is the last of the new material. Um, the plan is to have Zoom office hours on Tuesday, but silly me, I broke the screen of my laptop. So on my laptop, I can barely see what's on the screen because I broke it. I don't know how I broke it. I just opened up the laptop and it was broken. And I'm going to see if I can have our tech people repair it. And I'm hoping that they will give me a nice, fresh new one as a loaner while they repair this one. So it's possible I will not have a laptop on Tuesday. And if I don't, I'll try to figure something out. But so there's a small chance we will not be able to do office hours. If we can't, maybe we can figure something out, or maybe we can just do it with on my other computer where I can't write on the iPad because my other computer works great for Zoom, but I can't attach my iPad to it. So I'll figure it out. But currently, the MacBook that my school district gave me, it has a broken screen. I wish I knew what happened. It was pretty devastating when I opened it up, and I'm like, oh, wait, that's bad. So, so if I need to know what's on my screen, I'm just gonna have to look over, and it's hard to find the buttons to get things to do what they're supposed to do. So today we're going to be doing lots of math. We're going to be learning two new calculator functions and maybe three new. I don't think, no, because we already did inverse t, right? Did we already do inverse t? I think so. So we'll get two new calculator functions today. And we kind of got through all of the what do our results mean in the last video in Tuesday. So now we're going to do all of the math behind it. And of course, I'm going to draw some gorgeous pictures because I am just the amazing artist. So we're going to go to 10.2. So 10.2 is we're going to do hypothesis testing with population proportions. We are not going to use binomial probability distribution. We absolutely could, but we're not going to. So we're just going to do hypothesis testing with our population proportion. I took that piece out because so many people struggled with the binomial probability, the PDF and binom CDF and all of that. I decided that it is not taking away from your knowledge or making it so that you can't do things if we don't use that method. Because it would be just giving you another method. So we're just not even going to do it. We're just going to do regular hypothesis testing with p-values and z-scores. That's it. And we're not going to do the binomial. And then in 10.3, we're going to do hypothesis testing with mean. And we will talk about, we're not even, the funny thing is, we're not doing this either. I didn't even realize it was still there. So really, it's not a ton. We have 44 slides, which is about normal. My guesses will be done 6:15, 6:30, which I hope is true because that's what I told my daughter, and she's bringing grandkids over. So we'll see what happens. Okay, so remember the p hat. So our point estimate, um, we use this when we use our point estimate when we have a sample. So when we take a sample and we have number of successes over number of trials. This is the same p hat we've been using for a while. This is just our little reminder with my little guy with his string around his finger. Also remember, so we can, if our sampling distribution is normal, we will use this new standard deviation. So when we're dealing with samples with our sample proportion, when we don't know the actual population proportion, or when it's an estimate or a prior knowledge or whatever, we use this new standard deviation or the standard error. We need to check these three boxes. You're going to be checking these three boxes on your test because remember the test opens on Tuesday. First, it needs to be a simple random sample. If it isn't a simple random sample or it doesn't say, if it doesn't say simple random sample, we're just going to write that we're going to assume it's a simple random sample. And even if it turns out to not be a simple random sample, you're still going to do the math because we still want you to do the math. I still want to assess whether you can do it. So Then we have this right here, NP times 1 minus P greater than or equal to 10. This tells us whether or not it's normal. That tests whether it's normal. And we can tell if our sample values are independent of each other, if our sample size is less than or equal to 5% of our population. So these are the three things we need to look at before we do our math. This is what I want you to check. Now, you're going to have questions that don't require you to do all of the steps that and I don't care if you check them, if all I say is, what is the critical value? I don't care if you show me all of these steps. But there's going to be two questions on the test, one of them for proportion and one for mean, that's going to say in your work on your note paper, in the work that you're showing, I want you to show me every single step of the hypothesis testing, and then you're going to write a conclusion. So these are things that I want in those steps. I want you to show me that you've tested these things, that you've checked these things. All right. So as this is all of this is still review. Um, so we have a two-tailed test. Two-tailed test is when it says something like different. If it says different, we will use the not equal to. A left-tailed test would be like less than, or would say decreased, or anything like that. Any of the words that are like less than or decreased or anything like that. And then our right-tailed would be greater than or increased, etc. So those are our three tests. And anything that has this little sub-zero, I talked about that before, that's like an initial value. So this is going to be like our assumed value, and we are assuming the population proportion is that until we prove it differently. We are assuming it's what it is until we prove something else with our sample. So this is all of the stuff that we talked about last week, and now we can move on. All right. So after you do all of this stuff and you determine what kind of a test you have, then we're going to deal with our level of significance. You will be given a level of significance. I'm not going to ask you to do any of these where you're not given a level of significance. Now, if you chose to do one in your final project, you're going to choose your own significance level. Most people just choose an alpha of 0.05, but you can choose whatever you want. So your level of significance is whatever I give you, and it's based on the probability or the seriousness. So they don't use it as the probability of making a type 1 error. They say the seriousness. How serious is it? How devastating is it going to be if I make a type 1 error? Are bad things going to happen? And so you need to change your level of significance based on that. So if it is really bad for you to make a type 1 error, you're going to make your level of significance smaller. You want your alpha smaller so that there's less of a chance of you making that type 1 error, because 0.01 is a smaller probability than 0.05. But they're going to give it to you. I'm going to give you that, so don't even worry about it. Okay, next. So this is our classical approach. We're going to calculate the test statistic. The test statistic is the z-score that we find with our sample. That is a test statistic. That's what that word means. Because I was talking before last week about how we created our confidence interval, and then we look for, where does my sample lie? Where does it land in here? Does it land in here, or is it out here? The z-score that we calculate using our sample is going to be the test statistic. So you're basically just calculating a z-score. You take the p hat from your sample, subtract the p naught from your hypothesis, from your null hypothesis. So p hat, your sample information, minus the assumed value, divide it by that new standard deviation or standard error. And we use p naught. We use the proportion from our hypothesis, from our null hypothesis, we use that for our standard deviation because we are assuming it is true until we show anything different. We are assuming that our null hypothesis is true until somebody shows us something different. All right. Once we're doing the math, it's going to make a total sense. So our critical value we find from our Z table, and that's just that number at the bottom. So at the bottom of my Z table, we are going to, however, use this one because it's basically the same thing. But remember that our confidence level was like 95% or 90%. Our alpha is given to us as the smaller number, as the 100% or 1 minus that confidence level. So if I had an alpha of 0.05, if it's left-tailed, it's negative. If it's right-tailed, we look at both positive and negative. Or sorry, if it's two-tailed, we look at both positive and negative. If it's right-tailed, it's positive. So even if you use your calculator to find it, you need to just know in your knower that a left-tailed is always going to be a negative z-score. A right-tailed is always going to be a positive z-score. I'll write this on a page in a little bit. A two-tailed is you're going to look at both the positive and the negative. Let me show you here. Okay, so take a look at two-tail. I have a negative z-score and a positive z-score. My left-tailed, see it's over here, so it is a negative z-score. And right-tailed, it's over here, so it's a positive z-score. So you can kind of see it on this diagram. Okay. So with our classical approach, which obviously I'm not going to tell you, hey, use the classical approach. Hi, Edith. We were wondering if you were going to join us. So happy you're here. We barely even got started yet. Haven't even done math yet. Okay. So the two-tailed test, if my test statistic is outside either more negative or more positive, if it's outside of those two values, more extreme, I like to use the word more extreme, then we're going to reject the null. If it's a left-tailed, we only look at it as if it's more negative than the z-score. And a right-tailed, we only look at it if it's greater, if it's more positive, if it's beyond that. And drawing the picture can help sometimes. Sometimes it's hard to visualize, especially when you're dealing with negative z-scores. So if my critical value is right here, and this is negative 1.96, and then my test statistic puts me at negative 2.08, it kind of shows, hey, that is beyond, that is not in my safe space. It's not within my confidence interval. It is out there hanging out by itself, if that helps at all. Drawing pictures sometimes is kind of the way to go. Okay. Now, after you find your test statistic and after you find your critical value, compute your test statistic. Once again, it's just a z-score using your sample data. So compute the test statistic. And then, okay, this is the p-value approach. Sorry about that. So classical approach, we compare the test statistic with the critical value. Sorry about that. P-value approach. We are just going to use the calculator function that I'm going to teach you. Because we are not going to use binomial, we're not going to use binom PDF or binom CDF, we are just going to use the calculator. The calculator will give you your p-value. If you want to use the p-value approach, just use the calculator. So let's just call it that. You can use the z-table if you want, but nobody wants to use the z-table, right? Yeah. Let's just use the calculator. So that's where I'm going with that. But with the p-value, if my p-value is smaller than the alpha, we will reject the null hypothesis. P-value less than alpha, reject the null. Okay, and I will tell you the funny thing that I teach my high school kids, because high school kids are a little silly, but we're adults and we can be a little silly. This is what I tell them. This is how they remember it. If the P is low, reject the hoe. If the P is low, reject the hoe. This is what I teach my high school kids. They remember it every single time. So if that P value is lower than your alpha, you're going to reject the null hypothesis. I'm going to give you a second to write down my great wisdom. I admit I did steal it from somebody, but I loved it. Somebody put it online in some forum I was part of, and I'm like, that is brilliant. I immediately took a screenshot of it. I'm like, this is great because you're not going to forget that. The P is low, reject the hoe. Everybody likes a good rhyme. All right. So this, says use a statistical spreadsheet or calculator or whatever. We're going to do that. We're going to use the calculator. You're going to get two calculator functions today. And then I'm going to show you some places to go for your review for the test for next week. So p-value is less than alpha, reject the null. Then you're going to state your conclusion. So I did grade I graded the labs. And for the most part, they looked great. There were a couple little things here and there. Really, really important though, when you state your conclusion, you need to state your conclusion in the context of whatever the story is. Because sometimes people are going to skim through all of the lovely things that you write about what you've calculated and all of that. All they're going to read is your conclusion. And so when I read your conclusion, I want to know what the story was about. I am 95% sure that the actual proportion of people who vacuum their floor every day is between 46 and 52%. There you go. That was just something I thought of because I noticed that my grandson spilled cereal on my floor and I need to vacuum it. It was a crazy morning. So I'm like, there's a honeycomb on my floor. I must need to vacuum. So there you go. That's what happened. Oh, I'm froze. Am I still frozen? I'm good. Okay. Did we miss anything? We good? Okay. All right. That was 5:19. That was a couple of minutes ago. Okay. We're good? Okay. All right. I keep wondering if maybe it's because so Edith, you missed it, but I broke my MacBook screen, the one I normally use, and so I don't see everything on my screen right now. Yeah. Okay. Hey, we're gonna do some math. Um, in 1997, 46% of Americans said they didn't trust the media when it came to reporting the news fully and accurately, fairly, whatever. 2007 poll 1,010 adults nationwide, 525 stated they did not trust the media. At an alpha of 0.05, is there evidence to support the claim that the percentage of Americans that do not trust the media to report fully and accurately has increased since 1997? All right. So I usually start by writing my hypothesis. I don't care which order you do the beginning steps, the before math steps. I don't care which order you use. I usually start with my null and my alternative hypothesis just because I'm like, okay, what are we doing here? So first thing I'm going to do though is get my p hat. I'm going to write it up here on top. 525 over 10. I need to go grab my handheld calculator. Okay. My p hat. Uh-oh. I'm going to do 0.52. Are we all good with that? It's 0.5198. I'm just going to say 52%. We're not going to mess with all the extra. Okay. So my p hat is 52%. So my null and my alternative hypothesis, my H naught is that p equals 0.52. So it says, is there evidence to support the claim that the percentage of Americans that do not trust the media has increased. Increased means right-tailed. So my alternative hypothesis is that P is greater than 0.52. So remember, the only thing that changes is my 0 changes to a 1 and the sign changes. The number stays the same and both of them say P. Because we're dealing with proportion, both of them say P. Okay, so I'm going to do every step that I would expect you to do on your test because you are going to, on your test, you're going to show every single step of a hypothesis test. So I'm going to show you every step that I expect, okay? Except for if you want to use the calculator function instead of doing it by hand, you're more than welcome to do that because we don't all want to do everything by hand. Okay, so is it a, it does not say that it is a simple random sample. I'm going to write this up at the top because I don't have a lot of room. Assuming random sample. Because I went to 46%. Oh, you are so right. This is why I keep you around. Thank you. What would I do without you? We are doing 46%. My goodness, what is wrong with me? I had a teacher in college that used to give things called borderline bonus points, and she would keep track of them in the book. And whenever we either found a typo on her presentations or corrected her math or corrected something like this, she'd put these bonus points. The bonus points only counted if you were really close to the next higher grade. So, for example, if you were at an 88% in my class and you had collected enough bonus points, that would bump you up to an A. And she used to do this, and I've considered that a few times. I'm not quite that bold yet, but I thought it was really cool. So you just earned if we really did borderline bonus points, you totally just earned one. Okay, that's where I was going with that. Anyway, okay, so we got that. So we are assuming simple random sample. Next thing we're going to look at is it normal? So we're going to do NP times 1 minus P greater than or equal to 10. I'm going to just write this here. You don't have to actually show the formula. I'm just writing the formula down. So I'm going to do N is 10 or 1010 times P, which is 0.46 times 1 minus 0.46. Is it greater than or equal to 10? Oops, say here. Equals. I'm assuming it is. It would be really weird if it wasn't. Times 0.46 times whoa, what's wrong here? What did I do? 10 times 0.46 times point. Oh, it's just because I did 10 instead of 1010. I put it in my calculator wrong. 1010 times 0.46 times 0.54. Okay, that is greater than or equal to 10. Good, we checked that. It is normal. So we're good. So we're assuming a simple random sample because it doesn't say. We checked that it is normal. NP times 1 minus P is greater than or equal to 10. The next thing we're going to do is say that 1010, what is my problem? 1010 is less than 5% of our population. 1010 is definitely less than 5% of all Americans, correct? So I checked those things. I checked all three of those things. I wrote my hypothesis down and I checked those three things. Now I'm going to find my critical value. The critical value is the same thing the critical value was in with our confidence intervals. It is the edge of that confidence interval. It is how far can I get away from this proportion right here and still be a usual amount, still not be unusual. How far away can I get? This is greater than, so my critical value is going to be positive. So my Z sub alpha. It's not alpha divided by 2 because it's not alpha divided by 2 because it's just a right-tailed. So let's go over to our Z table. So we are looking at 0.05 and it's right-tailed. So my critical value is 1.645. You don't have to tell me, looked at Z table or used calculator. I know where you find your critical value. Don't worry, just write it down. So you don't have to give me an explanation. You didn't do math to get there. Just write it down. Write down your critical value. I don't even care if you ended up using inverse norm. Just write down the critical value. Unless you want to tell me, that's fine too. So this is my critical value. I'm going to write the words here. Okay. So now we need our test statistic. So yes, Z sub alpha. Oh, how to find it with the TI-84? Okay. All right. So my TI-84, I'm looking for, so when I find it with my TI-84, I'm using inverse norm. It is going to give me a negative value because I'm going to put 0.05 in there. But you just need to know in your knower that it's positive because it's right-tailed. This is just something we know. So second vars, and you go down to number 3, which is inverse norm. And I could put 0.05 because that's my alpha. And we leave 0 and 1 because these are z-scores. And because you guys don't have left, right, and center, left is the automatic, which is fine. Then hit enter. And so this gives me, if I rounded it, it's 1.645. It's the same value that we had. And I'm going to look at your work. If you wrote down negative 1.65 or 64, you rounded it to that instead. As long as you write down that that's the critical value you're using, I'm okay with that. But I want to see that that's what you're using rather than 1.645. Write it down. Okay. Next, now we need our test statistic. Our test statistic is the z-score we find using our sample data. So I'm going to write down the formula. We had it on the other screen, but I'm going to do it anyway. So it's p hat minus p naught over square root of p naught times 1 minus p naught divided by n. So it is just our sample, our point estimate with our sample minus the percent that they give us, the proportion they give us, divided by that new standard deviation. So what this is going to look like is this is when I use 0.52, oops, 0.52 minus 0.46 divided by square root of 0.46 times 1 minus 0.46 divided by 1010. If you are really careful with parentheses, you can put this whole thing in the calculator at once, put parentheses around the numerator. Otherwise, you're going to get something super funky. So if you're putting it all in your calculator at once, put those parentheses there. So point, or you can piecemeal it out. You can do it piece by piece if you're not comfortable with all of the wild parentheses. Equals 3.83 is what I got. I'm going to put an arrow there. Test statistic. Is that what you guys got? I'm going to give you a second to make sure. Okay, good. So I'm going to draw the picture. You don't have to draw the picture unless you want to. I'm just kind of doing it to illustrate here for you. So what I'm doing, what I'm checking is, here's my thing. So 1.645, this is my Z sub alpha, which is 1.645. Your test statistic is my test statistic more to the right or to the left of that z-score? It's to the right, right? It's actually like way out here, like way in the tail. This would be a z-score of 3.83. So since my test statistic is beyond my critical value, we are going to reject the null hypothesis. I'm going to let you write all this down because I'm going to erase it. And then I'm going to write the conclusion because I don't have enough room here. But I want you to, I'm going to erase all this in a second. Actually, I probably could fit it. Hold on a second. As long as you don't mind me put it, as long as you don't mind it looking a little bit ugly up here, I'm going to just write it right here. Get a different color. I just love colors. Sometimes I get bored and just have to choose random colors. All right. So what I'm going to say is, since our test statistic of test statistic, I'm just going to say what test statistic is larger than the critical value, we have sufficient evidence that, and I'm going to run out of room, the proportion of Americans who, I'm just going to say who do not trust the media. A second here. Do not trust the media is greater than 46%. I'm going to have to go down the side a little bit. Therefore, I'm going to put 3 dots. So these 3 dots right here in math talk, they mean therefore. So therefore, we reject the null hypothesis. I'm not going to write hypothesis out because I ran out of room. So since our test statistic is larger than the critical value, we have sufficient evidence that the proportion of Americans who do not trust the media is greater than 46%. Therefore, we reject the null hypothesis. You can, I'm not asking that you make it super long-winded or anything, but you could, even if you just said to me, the test statistic is larger than the critical value, so we reject the null hypothesis that, or I want you to say something about the proportion of Americans that trust the media. Your wording does not have to be perfect and beautiful. Here's what you must have in your conclusion. You must have how you know, or what showed you, what evidence showed you. And I don't care if you give me bullet points, you do you. What evidence showed you that we should reject the null hypothesis? Here it was that my test statistic was greater than the critical value. That's my evidence. Tell me what the evidence is. Tell me that it mentioned the story. Mention what it is that we showed. So we have evidence that the proportion of Americans who do not trust the media is greater than 46%. Talk about what we know. Talk about what our thing is, what we're denying or whatever. I want you to say the words, we reject the null hypothesis, or you can say we fail to reject the null hypothesis. Make it very clear. So it's going to ask you to show all the steps of a hypothesis test on in your notes for the test. Show me all of this stuff. Show me all of this stuff up here and show me your math down here if you do it by hand. If you don't do it by hand, write the calculator function you use and then copy down what's on the screen afterwards. Just copy what's on the screen so that I can see your outcome. Are you good, Edith?
I'm just laughing because I never, until this moment, understood what you meant by what calculator function you used.
Yeah.
I'm just laughing at myself. So
Okay.
yeah.
I'm just checking because you were like,
I know. I couldn't believe that.
It's
Okay.
all right. It's all right. So yeah, so just write like I'm going to show you the calculator functions in a minute. You don't have to do all of this math. You are going to have to find the critical value on your own. The calculator doesn't know what critical value is, but it will give you your test statistic. It'll give you that z-score. So you're going to take the z-score it gives you and compare it to the critical value. It'll also give you a p-value. And so then you'll take that p-value and compare it to your alpha. So this is what it's going to do for you. Okay. And then what it's going to do is says show all the steps for your hypothesis test in your work, and then all your typing in the box is your conclusion. That's what in the on the test, all you're typing in the box is your conclusion. This light green that I put up here, that's what you're typing in the box. So I'm going to see this lovely stuff typed in the box, and then I'm going to pop over to your work. I always look at your conclusion first, and then I pop over to your work and I read through and make sure that your work supports the conclusion you gave me. So that's how I grade these. And then I'm like, wait a minute, did they also include testing if it's normal, seeing if it's a simple random sample? Because these problems are going to be worth 10 points. So I want to see every little step. And if you didn't, feel free to show me extra. I don't care. But don't spend a half an hour on this problem. I don't want, if you have all of this or in this part, this stuff right here is the calculator function right here. Calculator. That stuff right there can be shown with that's your calculator function right there. Absolutely okay. All right. So I'm going to go to where they printed their stuff in just a second. I'm just trying to be super transparent about what I'm looking for. Okay. So they tested it said they say this is a simple random sample, but the story didn't tell us that at all. So I like the word assume in that case. Shows me that NP times 1 minus P is greater than or equal to 10. Talks about the sample size, so we're independent. They did their sample proportion, their p hat. They found their z-score. They did all the stuff that we did. And then it is a right-tailed test, so we compared those two things. Yes, we're rejecting the null. This is all the stuff I just did, but they have it typed out. And then that they checked the p-value. We're going to do the p-value in a second when I give you the calculator function. We will, I will show you the p-value in just a second. So just hang in there. And then there's sufficient evidence. They don't, see, this is why I make it clear what I'm looking for because they don't tell you how we know. They don't tell you, and they don't say reject the null. I want to make sure, I want to know that that's what that you know that's what you're doing. Theirs is a little bit less robust. So, okay. Now, let me show you the calculator function. You are going to be so happy with me when I show this to you. I'm going to pop back over here because I want the information. Uh-oh. Okay. Okay. This, uh, here is your one prop Z test. Is that where we're going? Hold on. Yes, one prop Z test, one proportion Z test. This is your calculator function. It's stat tests, one prop Z test. That's where we're going. Okay, let me get you there. Okay, so I'm going to I'm going to clear this out because that's just me. Click on stat, arrow over till we get to tests, and it is number 5. One prop Z test. The thing I like is it says prop. We're dealing with proportions. It's a hypothesis test. It says the word test on there, mentions Z scores. It's perfect. Okay. I'm going to hit enter. Okay. It wants our P naught. Remember, our P naught is the proportion they gave us. So that was 0.46. The X value was the number of successes we have, which was 525. The N is the sample size, which was 1010. Okay, and I'm going to tell you something. Most of the time, I choose the wrong one down here. I almost always choose the wrong one. You can tell if you choose the wrong one by your probability just doesn't make sense. Like this one, you can 0.52, which is what we got, is pretty significantly larger than 0.46 in our things here. So I'm going to probably have a very small percent. It's probably going to be really close to alpha. So if I get something that's super large, like a 0.995 or something, I probably chose the wrong one. So what we're looking for is greater than our P naught. So I'm going to choose this one right here. We're looking for our P naught. We think that it's greater than our P naught. I think that's correct. I just choose the wrong one frequently. We'll see. Fingers crossed. So once again, our P naught, which is the population proportion that they gave us, what we're our null hypothesis is, we have our successes and our sample size. Hit my calculator. Yep, see, okay. Good. It's a really small number. It doesn't look like a really small number, but remember, if I have a whole number before the decimal, this is scientific notation. So see my z-score, 3.8. That's what we got. We got 3.8. And they don't round, so it's going to be slightly different, but we got 3.8. My p right here, right, my p-value. Remember when I think I talked about this before. Maybe I didn't, though. If it has this e -5 at the end, this is scientific notation. It is telling me to take this decimal and move it to the left 5 places. So when I move it over, I have 4 zeros and then 6.8. I'm going to round to 6.86. So this is a very, very small p-value. Super, super small. See, it also gives me my p-hat. It tells us it's 0.52 is what we got. So I'm going to show you what this looks like right here. So this was 6 point, I put a point in there. Wasn't supposed to do that. Okay. This was 6.86 e -5. So I took this decimal and just went 1, 2, 3, 4, 5, 0, 0, 0, 0. The decimal's right there. Just move it to the left 5 places. That's what this tells me to do. This is saying, because we did 1 E99, remember that? That was 10, it's 1 times 10 to the 99th power. This is 6.86 times 10 to the -5 power. That's what this is. Gives me a very small number. This is practically 0. This p-value is practically 0. It is definitely less than my 5% alpha. Therefore, I reject the null. So instead of saying our test statistic is larger than the critical value, you could say that your p-value is significantly smaller than your alpha of 0.05. Therefore, I reject the null hypothesis. So you can mention that your p-value is smaller. I don't care when you're doing your hypothesis testing on your test. I don't care if you use or test statistics or p-values. I don't care. You choose. Whichever one you're more comfortable with as you do your homework, you're going to say, I like this better because my open math will tell you which one to use. But they're both here. That gives us both. The nice thing, though, about using the p-value is I don't have to look up my test statistic, right? I don't have to look it up because I have a p-value and I just compare it to the alpha that I already have. That's one reason I like that. The reason I like the test statistic and critical value, pretty much the only reason is I like the visual of seeing that it is more standard deviations away from my original proportion than the critical value. I like that visual of it being farther away. That's like the main reason I like that one. But otherwise, you use what you want. Questions about proportions with hypothesis testing? As we're going to jump into means in a second. Okay, let me go back to where we were. Okay, yeah. All right, so we are done with 10.2. You have enough information to do 10.2. I highly recommend you just use your calculator. I would just write this stuff down right here. I would say one prop Z test, here's the results. If I was doing this on a test, if I use one prop Z test, I would just write one prop Z test, write these things down. Don't write every single number you see. You can write 0.5198 or 0.52. I don't care. You can write, instead of writing P equals 6.85866 E negative 5, you could actually write the 0.00. I mean, it doesn't matter either way. You write what you want to on those, but go ahead and round. You don't need to write every single number on there, especially since I know sometimes 90 minutes goes by really quickly on the test. So just do what you're comfortable with. Okay. Questions about calculators or anything you need to show or anything like that? Okay. Let's jump to 10.3. Oh, I guess I should probably go back to my PowerPoint. So 10.3, we're going to be testing the hypothesis regarding a population mean. So it's kind of like when we created our confidence intervals with proportions and then we did it with means. This is the same thing. We're still going to be creating confidence intervals, but it's just mean instead. This right here, this right here is going to be my test statistic. So they're going to give us a mean that they think is true. I'm gonna write this down. Test statistic. This right here, they're gonna give us a value that they think is true, and we are going to calculate this test statistic based on our sample. And we're gonna compare it um, the same way that we compared the critical value Z score with the test statistic. This right here, we're going to use n minus 1 degrees of freedom for our critical value, just like we did with our proportions, or just like we did with our confidence intervals. You're going to use n minus 1 degrees of freedom for your critical value. Okay. I will show you every single thing that you need to put on your paper when you are doing this problem, the problems like this. I'm going to show you everything you're going to put on your paper. Okay. First, I'm going to rush through this because you don't have to reiterate it for me. So remember that our t distribution is different depending on our sample size or degree of freedom, that it looks a lot like a z distribution, but when we have smaller sample sizes, we have more room in the tails. Remember that? So it doesn't look quite the same as a z distribution, but it's going to get really close to zero, but never equal to it. It's still normal, but it's not as nice as the Z distribution. As our sample size gets larger and larger, our T distribution looks like the Z distribution. With larger sample sizes, our T score becomes a Z score. Okay, I'm going to move on to this. So here's what we're going to test. This is the things that we need to check before we test our hypothesis. Is it a simple random sample? If it doesn't say, then you need to just assume. I want you to say, we're assuming a simple random sample. Okay. Um, so either they either tell us that our population is normal or our sample size needs to be greater than 30. If neither one, I want you to state that you don't know whether or not it's normal, and then say because of small sample size or something, but still do the math. Okay. So if it doesn't tell you, so I think on the test, I made it pretty small. I made it like 7 or 8 data values. And so I don't remember if I say that it's a simple random sample. I have no idea. I don't remember. And I'm probably going to rewrite it anyway because I do that. Um, but if it doesn't say it, say if unknown if the population is normal, but continue to do your math. Are the values independent of each other? Remember that our sample size needs to be less than or equal to 5% of the population. So check these three things. After you check those three things, then you can start doing your math. But I want to see that you checked those three things. Because if you were out in the wild doing this on your own, for whatever reason, you would have to do that in order for it to be a valid hypothesis test. And obviously, we don't see that and when people give us conclusions. But if anybody decided to go back and check what you're doing, make sure that you've done those things. Okay. Same thing with the other one. Two-tailed is if it says different. Left-tailed is if it says less than. Right-tailed if it says greater than. We are only doing means. We're not doing standard deviations. So it's just going to be mu equals whatever the mu naught is, whatever the value they give you. And then mu does not equal whatever that value is. The only things that change are these. Those are the only things that change. The symbol in between the two values and that H naught to H1. Those are the only things that change. I hope it's okay that I'm kind of rushing through this because it's kind of redundant what we just did. Okay. All right. So then it'll give you a significance level. It'll give you that level of significance. I do have a calculator function that will give you a test statistic, but this is how we calculate it. The calculator function will not give you the critical value. You will need your t-table for that. You'll need your t-table for the critical value. Okay. This is all the same thing. If it lands out in that critical region, the critical region is the area outside of your confidence interval. If it lands in the critical region, we reject. This is all the same stuff. That's why I'm just kind of rushing. Compare the critical value with the test statistic. If the critical value is more extreme than the test statistic, we will reject the null hypothesis. If it's not as extreme as the test statistic, we fail to reject. Okay. All right. P-values. No, do not attempt to use the table for the p-values. It is not fun. You're likely to have an error. Do not use the t-table for p-values. This says it right here, but don't do it. So we do not use the t-table for p-values at all. So just use the calculator. We're going to do test statistic by hand, and then we're going to use the calculator function. I will show you where that p-value comes in. But yeah, don't use the t-table. Okay. I'm just going to move on past this and we're going to do a math. Okay. Um, it says this is one of the reasons I said even if we don't know that it's normal for sure, that still do the math is because if it's slightly off normal, it's not a big deal. It's not going to hurt it too much. It is only if it is extremely not normal that it's going to cause problems. It's not a super big deal if it's slight departures from normal. It's not going to greatly affect things. So that's why it says it's robust. Don't worry, you're not going to be tested on that. I'm just kind of giving you the reason why. Okay, here's a problem. So we're assuming that the resting metabolic rate of healthy males in complete silence is 5710 kilojoules per day. And the researchers took 45 healthy males who were listening to calm classical music. Their average resting metabolic rate was 5708.07 with a standard deviation of 992.05. We're using an alpha of 0.05. We want to know, we're looking for evidence that the average of males listening to calm music is different than this. Since that word different is there, this is a two-tailed test. Because it says different, whenever it says different, this is a two-tailed test. So we are creating our normal confidence interval. Because it's two-tailed, we'll use T sub alpha divided by 2, just like we did with our regular confidence intervals within 9.2. So this is basically doing 9.2 and then just adding that extra step of the test statistic. But I'm going to write my hypothesis and then we're going to do all of our pre-steps. So my hypothesis, remember your H naught is like the status quo. It's what we're trying to show. We're trying to like, we're showing whether it is or is not true. We believe it's true until it shows it's not. Mu equals, what is it, 5710 kilojoules per day. I'm not going to be a stickler about whether or not you put the units up there. I like them there, but I'm not going to mark you down if you don't. I feel like that's just splitting hairs. So I'm not going to mark you down for it. My alternative hypothesis, because it says different, we use not equal to. We use not equal because it says different. This is my hypothesis. I'm trying to show that it is either greater than or it's less than, but it's not equal to. Okay, let's test all our things. Um, it does not say that it is a random sample. So we are going to, I'm writing this up at top again, assume random sample. My sample size is greater than 30. So since my sample is greater than 30, all right, wait. Yeah. So I can say n greater than 30, so it's normal. And in my AP stats class at the high school, I make them actually say by CLT, which was that central limit theorem. You guys do not have to mention the central limit theorem. Just tell me it's normal. Because my sample size is greater than 30, it's normal. Now, when you have the independent, my sample size is less than or equal to 5% of the population, so it's independent. These are the three things you must test and show on your test. Show that you checked these three things. Before you do your math, check these things. Even if even if for some reason it didn't pass, it's okay. If it didn't pass these things, still do your math, but just show me that you checked them. All right. The next thing I'm going to do is I'm going to look for my, I'm like trying to do all the easy, always try to do all the easy stuff first. We're going to find our critical value. I'm going to write critical value over here. My critical value, so my T sub alpha divided by 2, it's divided by 2 because it is a two-tailed test. That's why it's divided by 2. So we're going to go to so it's 45 healthy males. We're going to jump over to our T table. This one makes it a little trickier. But my T table, and it's divided by 2. Oh, I'm going to jump back over here. My alpha is 0.05, but because it's two-tailed, we're going to do 0.025. You remember this from confidence levels? Oh, I guess I have it underneath the thing here. Move it. I'll move it. Remember with confidence levels, we had to cut that alpha in half, right? So we're going to use 0.025. Let me go back over here. Okay. So we are going to be, whoa, we're going to be in this column and we're looking for 45. Let me go a little bit smaller. So the tricky thing here is that we don't have a 45 or 44. So I'm just going to split the difference here. So let me see here, 0.025. Stay in this column right here. That's the struggle with once you get larger sample sizes, you have to kind of guess. So I'm just going to take halfway between 2.021 and 2.009. Okay. 2.021 plus 2.009, then divide it by 2. I'm going to use, oh, hold on. I had my eraser on and bad things happened. Good thing you can't see it. So I'm going to use 2.015 because that's halfway between. I'm going to show you how to get this on your calculator. We've done this before, but I'm going to do it again. If I was using my calculator, I'm going to do second vars. We're going to use inverse t. Remember this from last week? Maybe not. It's okay. Not every calculator has the inverse t function, so you just get to estimate with the table otherwise. So if you don't have inverse t, just estimate with the table. Inverse t, my area, 0.025. Oh, that's not a 5. My degrees of freedom is 44 because n minus 1, remember, and then paste. And I use 2.015. Heck, look how good I am. It's 2.015. And it says negative, but because it's two-tailed, we're going to use both the positive and the negative. I'm going to write plus or minus in front of it. Look at how good that was. See, splitting the difference, I'm kind of wanted to show you the evidence that that works by just averaging those two numbers. It works and it's going to give you good values. So you're good. All right. So that's my critical value. Now let's calculate our test statistic. I'm going to write it down again. So it's x bar minus mu divided by s divided by the square root of n. Use parentheses if you're going to put the whole thing in your calculator at once. You'll do it like this. So let me write this down. Equals. We have our x bar, 5708.07 minus 5710. I mean, you can kind of tell by looking at it that we're going to have a negative z-score divided by 992.05 divided by square root of 45. Let's get some parentheses and things going here. $992.05 divided by square root of 45. That is a lot of parentheses. I got negative 0.013. That's really small. But did you get negative 0.013? I'm going to write it again. I believe that that's correct. I believe it's the correct number. So in this case, my test statistic, I'm going to put an arrow there. Test statistic. My test statistic is inside the confidence interval, right? It lands in my confidence interval. If I was to draw it, this is negative 2.015. This is 2.015. My test statistic, it's like right here, it's just to the left of the mean, negative 0.013. It is like so close to the mean. Okay. It's so close to the mean. It clearly is not unusual. It is inside my confidence interval. Now, when we put this in our calculator to get our p-value, I'm going to let you know the probability is going to be pretty high. Because it is practically at the mean, the probability is going to be a very high probability. This is one of those common sense kinds of things, and my probability is going to be a high number, right? The probability of getting a value that is that close to the mean is probably pretty good. I don't know what the number is. My guess is probably going to be like 88% or something. It's going to be huge. We'll see, but I think it's going to be a big number. So now I need to write a conclusion. So if you're doing it by hand, I want all of this math that I just did here. I want to see it all. You don't need to tell me how you got your critical value. I don't really care about that. And I care about it, but I don't care if you put it on your in your work. You don't have to show that. I'm gonna get it. color that's going to stand out. Let me see here. Okay, let's get a color that's going to stand out. Oh, let's just do blue. I haven't done blue. Okay. Let me see if I can fit it in here. So since our test statistic is not um mm, 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 mm. I would almost say maybe since it's not beyond our critical value or less than is not outside the uh trying to think of a good is not I'm going to say beyond, not beyond. I like beyond our critical values. Um we cannot we do not have sufficient evidence to suggest the mean RMR. I'm not going to write the whole thing about men. Excluded from? I kind of like that too. That's good. That's a good word. Um, is different than 5710 kilojoules per day. This might not fit. I'm going to put the little three therefore dots. Therefore, we failed to reject the null hypothesis. There we go. Since our test statistic is not beyond our critical values, we do not have sufficient evidence to suggest the mean RMR is different than 5710 kilojoules per day. Therefore, we fail to reject the null hypothesis. So this is what I want to see in your work, unless you use the calculator function, which I'm going to get there in a second. Questions about the math part. Are we feeling okay so far? It kind of isn't different than what we've already done, right? It's just we're applying it in a different way. It's not super different than what we've already done. Okay, pretty all right. Okay, I get that. We are going to have one more example with our the means. We're going to have another example of that. What I'm going to do real quick though is I'm going to give you the calculator function. The calculator function is t-test. It's I'm going to write t-test. So it's stat tests t-test. And this is going to be similar with our confidence intervals where you can either enter data or you can enter the information. And since I only have stats right now, I don't have data, I'm going to enter it that way. And then my next example, we're going to just jump straight to the calculator function. All right. So I'm going to clear this out. So we're going to go to stat, arrow over to tests. T-test is your second one here. Is it even in here? Let me see. I'm trying to see if I have a page that actually has that calculator function on it. There's a whole lot of, man, I have a ton of pages on here that don't say anything. A second here. Okay. So I'm going to go to t-test. So we don't have data. We have stats. So that's where I'm going. Go move it over to stats and enter that. My mu naught is my null hypothesis. So it'd be 5710. My X bar, so that's 5708.07. Now it wants your sample standard deviation. It gives us that 992.05. My sample size was 45. And since it's different than, there's no question which one we need to choose, right? Because different is the only one that's not equal to. It's the only way I'm not going to accidentally choose the wrong one. So whenever we say different, it's not equal to, and then I'm going to go down to calculate. Draw gives you a nice, pretty normal curve and shades it in and everything, but don't do it. It's cool and it's pretty, but it's not going to be helpful. So here's what it gives us. It tells me, look, it shows me my alternative hypothesis. It shows me my t value. This is my test statistic. This is the same one that we calculated. That's my test statistic. I thought the probability was going to be like 89. It is really high, but that makes sense because it is practically sitting on the mean. So if you ended up with a test statistic that was negative 3.4 and then you had a p-value of 0.98, you clicked the wrong button of the greater than equal to or greater than less than or not equal to. But if you have a test statistic like this that is super close to my mean, I'm expecting a large p-value. It's just kind of a common sense thing. And this tells me my X bar, which we already have in our sample. So you can look at this p-value, and that p-value is not less than my alpha. So I'd failed to reject. This t value here is not outside of my confidence interval. See, I guess you could write that also. You could say, since the test statistic is not outside the confidence interval, those are good words. You can use those also. Um, this gives us the information that we need. This is what you would write if you're using the calculator function. You don't need to write the X bar and the SX and the N equals 45 because we have that information. Just give me these three things. Give me even write T test, and then just give me this top piece right there. Those top three things. Because this one, the top one, I kind of want that because if you chose the wrong value, like let's say you chose less than instead of greater than, I'm going to see that when you write this, if that makes sense. And that you're going to lose less points because I'm going to say, oh, they chose the wrong one. And so you might lose like a half a point for that or something. Maybe a point. I don't know. Depends on how I'm feeling. That's the thing is grading is kind of subjective. I try to grade when I'm in a good mood because if I'm in a bad mood, I find I get a little more critical when I grade. So I always try to make sure I'm in a good mood when I grade. It's It's just nicer. Okay. All right. Yeah. She says yes, pretty all right. Are we kind of okay here? We okay to look at another one? Okay. They have all the stuff that we have here, so I'm just going to move on. Yeah, it says t-test function on there. Okay. Uh, so what this tells us, and if you're looking at the PowerPoint, you probably have these screens right here. I'm not going to ask you to put it in your calculator and say whether or not it's normal. I'm not going to ask you to do that. We are just going to, you're going to state like right here, my sample size is less than 30. And I just tell me that the sample size is less than 30 and you don't need to look for outliers. I don't want to put that on you because you know how to look for outliers. I don't want you to have to do that extra math. Just acknowledge that the sample size is less than 30 and it doesn't state that the population is normal. Just write that on there. Because what we do in real life, what we would tend to do is we would use our calculator or Excel to create a box plot or a scatter plot or a histogram so that we could kind of see whether or not it's normal. I'm not expecting you to do that. That's just what we do when we're out in the wild. But I don't want you to take that time out of your test time when I've already tested you on that. So I'm not looking for that. So we're going to take the first thing, I'm not going to write these down because I want to focus on the calculator and all of that, but we're going to talk about them. Does it say there's simple random sample? Yes. He randomly selected 8 state quarters. That's random. Good. Um, my sample size is 18. It's less than 30. It does not state it is normally distributed. But let me show you. Take a look at my box plot. It looks fairly normal. So I'm just telling you that that's what my box plot shows. So I can say it's normal. You're going to say that we can't assume normal because we have an 18. It doesn't state it's normal, and we have 18 sample size. That's what you're going to say. 18 is definitely less than 5% of the population. We're good there. My null hypothesis, you have to write your hypothesis. Make sure you do that. My null hypothesis is that mu equals 5.67 grams. That's my null hypothesis. My alternative hypothesis, that's a 1. My mu, let me see, different, not equal to. There we go. My mu, we're not equal to because it says different. All right, critical value. I'm going to write it up here on top because I'm up here. Critical value. All right, we are looking at alpha equals 0.05. So we have T sub alpha divided by 2. We're going to do 17 degrees of freedom because because this is a T value, 17 degrees of freedom, 0.025. Are we all good? Okay. 0.025 is right here. 17 degrees of freedom. My test statistic is 2.110. If you want to use inverse T, absolutely go for it. Use your inverse T, embrace the inverse T, go for it. Just don't forget 17 degrees of freedom. Okay, we're good so far. Go to the calculator. So we did this with our confidence intervals. We did this where we put the info in our lists. We're going to do that again. We have all of this data. I'm going to put it into my list. So I'm just going to type those in. I'm going to tell you that on your test, I am giving you a list rather than giving you the information. So you're going to be using the data. If you don't want to type it in your calculator, if you want to do everything by hand, I get a lot of people every term that do it by hand, use your one variable statistics to find the mean and the standard deviation. Okay, 5.62, 5.73. I'm going to say it again. If you want to do it by hand and you don't want to use t-test, then use one variable statistics, one var stats to find your mean and standard deviation. But if you're typing it into your calculator anyway, why not just use t-test? If you have to type it in anyway, right? Why wouldn't you just use t-test? But there is something a little bit elegant about calculating your own test statistic. I get it. I like to do it by hand sometimes just because I mean, I like to do math by hand and I am kind of a weirdo. I did choose to teach math, so take that with a grain of salt. I must have typed one double because I have an extra value. So let me go take a look. 5.7, 5.67, 5.73, 61, 767, 65, 62, 73, 65, 79, 73, 77, 71, 7, 76, 73, 72. Okay, maybe not. Nope, that's 18. All right. Got them all in there. Are we good? Can I move on? Got them in there? All right. Okay, so now that you have those in your list, the stat tests, go down to t-test. Remember, do not use the z-test button ever, ever. One prop z-test or t-test. We have data now, so I'm going to click on the data button. We have data. So I want data, enter. It asks me for the mu naught because it doesn't know what my null hypothesis is. So we do have to type that in because the calculator does not know what my null hypothesis is. It also doesn't know whether I have a left-tailed, a right-tailed, or a two-tailed. Leave frequency as 1, just leave it alone. Type in whatever list you're using. We're doing not equals here. And I'm going to go to calculate. Hit enter. Here's all my lovely things. Did I type the wrong thing in there? Oh, you're right. Thank you. My goodness, what is wrong with me? 5.67. This is why I keep you around. See, look, another one of those borderline bonus points if I was handing those out. You would probably get like 5 every class. Okay. So 5.67, my t value, my test statistic, that's what this is. The test statistic is 2.75. My p value is 0.014-ish. This is my X bar. That's fine. There's my standard deviation. So it gives me those. So you are going to write, I want on this one, because we didn't have the X bar and the standard deviation. Can you write all of those down, please? Give me all of this. I don't care about n equals 18 unless you want to, but give me all of this. So this p value is definitely less than alpha. My alpha was 0.05. This is less than alpha. We can reject the null hypothesis based on that. Or my t value, which is my test statistic, is beyond that 2.110 that we found. So I don't care which one you use to reject the null hypothesis. I don't care. You choose whichever one you want, whatever one you like to do, choose yours. And if you are using p-values rather than test statistic and critical value, you don't even have to find the critical value. Just use the p-value. That's the kind of nice thing about that. It's one less thing to write down. But once again, I love visualizing it. I can picture the curve and all of that. And if you want to write the curve, draw the curve, I love it. I love looking and seeing people using their tools there. So I would say that since my p-value of 0.136 is less than alpha of 0.05, there's sufficient evidence that the average weight of a state quarter is different from 5.67 grams. That's what, therefore, we reject the null hypothesis. Are there questions about this? I kind of love that chapter 10 follows chapter 9 because it's kind of like giving you another way to use that confidence interval that we already used. And it's almost like it makes it more important or more useful. And it's kind of like here I can like take guesses and say this sample that I took, maybe somebody took a poll, like a presidential poll or whatever. They're like, look, this candidate is leading 63% to 37%. And you take a sample, and in your sample, you only got that candidate had 43%. You'd be like, okay, let me do a hypothesis test. I think that it's actually less than that. And you could figure out maybe their sample was biased. With your hypothesis test, you can kind of show the other person's information might be biased because the probability of me getting that sample is basically nothing. So it probably didn't happen, and we probably need to take more samples. So there's things like that in real life that we can use hypothesis testing for, is because once they have their confidence interval, if your sample shows something very different, we're going to take some more polls. We're going to do a little bit more digging, if that makes sense. Okay. So questions on hypothesis testing with the mean. I know I have 7 more slides, but they're basically not 7 more slides. It's all just the stuff we already did. So are there questions about this? You need practice? Yes. So right now you understand, but yeah, I know. Hopefully my open math will be helpful. If not, you guys know how to find me. Okay, so this just shows they they said that this looks like it appears normal. They graphed it this way. They showed the box plot that it appears normal. You guys, I mean, obviously on a test, you can't use Excel. You can plot it in your calculator, but I didn't really show you that because I didn't find a whole lot of value since we use Excel. Just say that, it, we don't know if it's normal, but this is why. It's okay. And then our null hypothesis, our alternative hypothesis, it did all the math there. That's all this is the math that we already did. And then there, right there, the p-value is less than the level of significance. We reject the null hypothesis. And t-test on your calculator. I p-value approach is probably the easier one. Am I okay? It's probably the easier one, but you know, test statistic, you gotta kind of like it a little bit. All right. Sufficient evidence at alpha equals 0.05 of significance to conclude the mean of the state corners differs. So there we go. All right. I'm going to show you probably, so whenever I teach this in person, um, before I give them the test and I tell them how many notes that they're allowed to use notes on their test, most people, the only thing they bring in for this test is this thing I'm going to show you here in my open math. Just a second here. Okay. So in our last week here, week 8, well, I'm going to show it to you in here, I guess. Probably because that way you know how to find it. In week 8, get ready for test 3. There is this final review PowerPoint right here. Yes, we have handouts and they're great. This final review PowerPoint right here, this is our gold. This is the gold right here. I give you a confidence interval. Let me share this. Maybe. Okay. I give you a confidence interval handout that shows you all the stuff. Shows you the calculator function. It shows you all the formulas. It is really kind of lovely. Then I give you the hypothesis testing one. So it's 2 pages. That's all it is. On one side is all the confidence interval stuff, and on the other side is the hypothesis testing stuff. So if you print this off and you just write a couple of little notes on it for yourself, you now have generated this note. Because remember, you're allowed to use any notes you have generated yourself. So if you print this off and then you write a couple little notes for yourself, now I'm going to tell you, this right here does work, but I would not do it because binomial stuff it seems to be everybody's Achilles heel. So you absolutely can just cross that off and not use it. But this is how we would calculate the p-value, but I don't recommend it. So just don't even use it. Maybe that's what you wrote on it. Maybe when you printed this off, all you wrote on it was crossing off the binom PDF or CDF, but yeah, see, I know it's that's the thing is you know the stuff and then you sitting in class you're like, yeah, this makes sense. I can do this. You open up my opening math and you're like, is this what we learned in class? What the heck is going on here? I assure you I'm teaching the same stuff. I assure you, I am teaching what's in your homework. It just all kind of looks a little bit different and is worded kind of funny sometimes. But I'm going to make sure over the next few days that I'm checking my messages. You send me messages, send me problems you have. I'm happy to help you. And currently, then before I go off of recording, currently the plan is from 5:30 to 6:30 on Tuesday, we will have office hours. But as I said at the beginning, before you got here, Edith, I broke my computer screen, um, and I can't see much on my computer screen. I'm talking to the tech people at school tomorrow, and so that hopefully I can get a loaner or something. But it's quite possible they're not going to give me another computer and they're just going to take this and fix it and then give me it back when it's done. So if I don't have a computer, we'll have to figure something else out or not, but I'm going to try to do everything I can to do it. So it's not a promise, but I'm going to do my best to have office hours on Tuesday. But hopefully we will because yeah, but with this, I could do it if they don't take my computer, but if they take my computer, that's a problem. So, any questions for while we are being recorded? Okay. I'm going to turn off the recording if I can find it. Where is it? Okay, stop recording. Where's that button? Uh-oh. I don't know where it went. Let me quit sharing. Maybe if I quit sharing, it'll show up. It's because I can't see my screen. I can't find where things are because I